I am developing open source software for network traffic monitoring since about 20 years. And today I'm not going to talk straight with one topic, but I want to divide the talk in two parts. The idea is to talk about traffic monitoring with Internet of Things and cloud. And then to show you what are the challenges and how the cloud, for instance, or content delivery networks have affected network traffic monitoring. In particular for people that are using Wireshark, and what type of things they have to keep in mind when doing this type of traffic analysis. Because the cloud is not just another way of deploying services, but it is also affecting the way services are delivered to people. And this is something to keep in our mind when we do our daily activities. So the talk will be divided in two parts. The first part is a sort of tutorial. The second part is more interactive. So like I've said, we started 20 years ago a project called NTOP. So if you go to ntop.org, you will see that the way we monitor traffic today is very different from what we have done 20 years ago with this user interface. And my daily activities is, in essence, to develop this application, to play with packets. Wireshark is very useful for me to develop applications because whenever there is a new traffic application, a new protocol to decode, it is a very, very useful tool to understand and to debug that. So it's not used by us for monitoring because it's more troubleshooting tool. So as soon as you have an issue that you have identified a problem in a system in a certain period of time, in a certain communication, then you go to Wireshark. But otherwise, we use it for development. That is probably not used very often by people. So during this talk, during the second part, you will see that I will be playing with some packet traces that I have collected. So if you want to mark this URL, so luca.ntop.org, SharkFest 2018, you can also play with me while doing that. These traces are coming from real use cases, so it is real traffic. It's traffic that I've taken from my network, from friends' network, from public network, where you will see interaction of devices, multiple devices, either multimedia or IoT devices. And the traffic is not special, so in essence, you can find it in many other places. It is interesting the way devices are interacting, and it is interesting, for instance, that some IoT devices are that simple that they try to protect themselves by doing, let's say, interesting communication that we'll be analyzing later. So this is the URL. Let's start. So the first part is a tutorial. Okay, it's more university-like tutorial. It's not very, very complicated, but at least I want to position. I want you to understand that sometimes before looking at the traffic, we should not believe to what we see. When I'm teaching to my students, I'm telling them that packets are simply electricity that is moved on a wire, so that everybody can craft a packet from the MAC point, from the MAC address to the IP address, to the port, the content. So it is true that packets never lie. But on the other hand, this is not fully true today, because if you look at the traffic, you should not believe what you see in the traffic. And I want to give you some examples. So this is very important. So to have some sort of good way of analyzing traffic. So why I'm telling you that? Because over the past few years, in essence, in the last decade, there have been some changes, very important changes. So if you buy a manual that talks about, or a book that talks about TCP/IP, you will see that the protocol, the name, the ports are kind of the same. But if you look at the traffic today, and if you look at the traffic 10 years ago, you will see that the way traffic is sent has changed. First of all, because of the protocols. So in the past, there was, when I learned TCP/IP, there is always this communication, client-server. The teachers said there is only one IP address, public IP address in the world. So if you're sending this IP, you're really sending to that machine located in that place. And then with peer-to-peer, things have changed. Another interesting thing is the content delivery network. So when you access a website that is very popular, the content of the website are not all the time local. So if you go to apple.com or Netflix, you don't access Cupertino. But those files, part of those files might be local, part of the files might be remote. So it's very complicated, and I'm going to talk about that. And the same for the cloud. And then users. Okay, in the past, they used to have terminals or PCs, pretty static. And then we moved to laptops that were partially mobile. And now we have smartphones. That is another way of interacting with the internet that has definitely an impact. So what I'm going to say now, I'm going to talk, is the impact of those changes in traffic patterns. So how those things have affected the monitoring activities or Wiresharking, and why we have to take them into account. So when a protocol was created 10, 20, 30, 40 years ago, the protocol was usually unclear. So these are typical examples. And the protocol was designed per application. So in essence, if you have to resolve an address, people invented the DNS. If you have to connect, SSH, and so on, and so on, and so on. So one problem, one protocol. And this is something good because, if you see SIP, it is VoIP, usually. If you have to synchronize clocks, use the time protocol, network time protocol. But then over the time, this simple model, one protocol, one activity, was lost. Was lost for many reasons that we are now going to analyze. And also, it was lost the simplicity. So if you look at those protocols, it is very easy to debug them. Let's say that security was not an issue. So if you look at those traces, you can find some of them in my folder. You will see that even if you don't understand what is really happening, you have an idea, who's talking to who, from, to very explicit fields, something very, very human, close to humans, let's say. So debugging was not that difficult. This was the initial idea. So one protocol, one thing. And then security was not an important priority because we were all close friends. But since the security started, the idea was not to create yet another protocol, but to take the existing protocol that everybody understood and to put a very tiny layer on top of it. So this is an example for email. So you will see that we begin in clear, as in the past. And then at some point we say, OK, fine. But now I want to talk to you over a secure channel. So we start moving to encryption. And another typical example is SSH that has taken Telnet, so the existing Telnet clear text protocol, and put another layer on top of it. SSH in a way is an exception because does not uses SSL or TLS if you wish. So it has created its own way of doing that. But in general, most of the protocol are just the old protocol plus SSL, simply adding yet another command to it. Binary protocols were not very popular. So if you think about two examples, Radius, DHCP, or even DNS, were not that popular. So people prefer to do something in clear text. The reason is that sometimes you need to be binary because it is easier to compress data, to represent the data in less space. So for instance, if you look at the DNS traffic, and you can decode DNS with Wireshark, you will see that many times when you ask for, let's say, google.com, the reply contains not just google.com, but also says that Google is an alias of something else, Google. The DNS of Google is blah, 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 Google. So instead of repeating Google, 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 Google too many times, inside the protocol, they put some sort of references to the initial Googles that was first seen in the packet just to save space. So the reason why people use binary protocols had a good reason. So it's not that people disliked text, but because there was a reason for instance, for compression. And a good way of doing that in a portable way is ASN1. But ASN1 is not that easy. So you have heard Gerald in the first day saying that a lot of ASN1 code was automatically generated by tools. And ASN1, even though it's still at 1, so version 1, it is very popular today. So if you look at 4G or LTE traffic, it's still coded in that way. So it means that it is not yet dead. Okay, so we have to survive with that, even though it is not the best protocol, I would say, because the coding is not that simple, but I mean, it still exists. So mostly text, sometimes binary. And then initially there was one protocol that was designed just to transport hypertext, so in essence HTML, that has changed many things. Because when the hypertext protocol was created, the internet was not very fully connected, let's say. So universities and people were connected to the internet, but they had public addresses. I've seen some stickers here on the tables that no NAT, so IPv6. I don't know if it's a good idea to move IPv6, honestly. I know that not everybody thinks that, but let's say this is my position. Because of NAT, okay, and because of the need to have a firewall to protect yourself because the internet was not that safe anymore, HTTP had a good success beyond the initial idea. So the initial idea of HTTP was just to transport images and HTML. But because firewalls had to be aware of that protocol, because of NAT, because addresses were not that popular. I mean, we had one address from your ISP, a few addresses. So if you want to buy more addresses, like today, is probably more expensive. So people said, but if we have a firewall and the firewall understands HTTP, why do I have to bother creating yet another protocol for my own activities? Let's use HTTP. And this is basically a star protocol, so it's used for everything. So in essence, today, if you see people, in particular at my university, when somebody has to create, an application that has to send something or receive something, in the past, my students used to do that on TCP. Now they use HTTP because there is a library. So you can send and receive. When I say HTTP, I mean HTTPS usually. So secure HTTP. So in essence, it was commodity. And this trend is still continuing. So if you look at the latest innovation on DNS, you will see that DNS over HTTPS is a way to go. And it is interesting. Try to find this one on Google and search for Cloudflare. So there is a browser, Firefox, that in the latest release is supporting that. So in essence, Firefox opens a secure HTTPS communication with Cloudflare. Over that communication sends DNS request. And then at the end, you will see, if you read this report, that it's faster than the standard DNS. It is faster because when you connect to Cloudflare, it takes a while because you have to negotiate the communication. But then once you are connected to Cloudflare, every address you are asking, in essence, is in the cache of Cloudflare. So instead of using the usual iterative process of resolving addresses, it is easier to go to one provider and to ask everything to it, even though you are not a customer of that ISP, if Cloudflare could be an ISP. So this to say that HTTP is no longer hypertext something, but is used for many, many things. So therefore, when you look at the traffic, you will see that many applications are using that, even though it's not the real protocol. And if you look at traffic like Netflix, Amazon Video, and so on, you will see that it's used also for streaming. In the past, the idea was to use RTP. So we do some sort of negotiation. I like you, you are my customer, I want to show you, my videos, and then I send you the movie. Now you do partial download through HTTPS, so you download in chunk because HTTP is now supporting that. And because of that, HTTP is also used in places where other protocols were initially designed for that purpose. So HTTP is becoming more and more popular. But HTTP is also changing. So if you have seen, there's a lot of activities in Wireshark development for supporting something called Quick, okay? That is kind of HTTP 2.0. But also, if you look at mobile phones, you will see, and if you go in the initial URL I gave you at the beginning of my talk, so luca.ntop.org/SharkFest 2019, you will find an interesting example. So this is one protocol called Facebook Zero that was designed by Facebook just to solve this problem. So whenever you have to use SSL, the initial communication, okay, needs a lot of packets because you have to send the key, I like your key, I send you my key. So in essence, you need 10 or more packets just to start the communication, and then you have to communicate. And in particular, for mobile phones in places where you don't have a lot of bandwidth available, this adds latency and moves a lot of data. So you're taking bytes out of your plan. So Facebook has created something called Facebook Zero that is supported by Wireshark. So you need the latest 2.6 or something. So if you have a previous version, Wireshark is not able to understand. So you will see that on the mobile version of Messenger, so you need Facebook Messenger, one of the latest versions on mobile phones, you will see that they're using this protocol. It is interesting because the number of packets that are necessary to set up the communication is very limited. Why I'm telling you this? Because if you say, I have a problem with messenger communication, okay, you try to troubleshoot the problem, and you can use Wireshark. Maybe it's a DNS problem. You don't resolve Facebook, whatever. If you capture some traffic from your mobile phone, so let's say you turn off 3G or 4G, you connect to Wi-Fi, and you connect the messenger traffic. You do the same experiments on your laptop, Messenger, and so on. So you log into Facebook. You will see that not only the traffic is going to different places, but the protocol itself is different because this one is used by the mobile application. Standard HTTPS is used by your Facebook application on the browser. So this means that mobile optimized protocols are also changing the way you debug your application, you troubleshoot your problems. Because when you have a mobile phone, even though, again, you are connected to your Wi-Fi, so you don't use your wireless operator, the problems that you are trying to address might not be the same, can be totally different. Even though you are accessing the same messages, even though here I'm sending you the same message that you will be receiving on your desktop application, the protocol is different. And these things are more and more popular. So we see a trend that is not driven by standards, but driven by the fact that when you access those contents over mobile phone, you're not forced, but let's say having an application like that, a protocol like that, it is better because you save communication, you save packets exchange that over the wire are very interesting. So you will see that with the latest Wireshark, you see Facebook Zero. So if you have an old version of Wireshark, you will not be able to identify that. And you see, all is in clear. Sorry, the certificate, part of the certificate is in clear, and everything else is encrypted, same as HTTPS. Another thing to take into account is the protocol nature. So there are two types of protocols in essence, store and forward. So you don't talk directly with the remote end, but you send your message to somebody, and somebody is delivering this to the final destination, or you have a client-server communication. So if you have to troubleshoot a problem, here we have seen good examples of people saying, okay, bring me your trace, I will show you what is the problem. And we talk about the window, this and that. And this is easy if I'm talking to you, so one-to-one. But if in the middle, there is another pattern of communication, so for instance, if you download a file through BitTorrent and your BitTorrent client is not able to download that file, what's happening? It's complicated. You don't know the peer where you are talking to, at least you cannot know that peer in advance, okay? And this is another point to take into account. So in the past, the communications were very easy to troubleshoot. So most of the examples you are seeing at SharkFest are like that. So you have A that is talking to B. You know the IP address of A, you know the IP address of B. You set a filter like IP SRC, blah, blah, blah. And you have this traffic. But if you want to troubleshoot, and I've never seen an example like that here at SharkFest, an issue with peer-to-peer communication. So let's say I'm unable to download my Ubuntu ISO image through BitTorrent. How do you troubleshoot that? Because this is very complicated, because you don't know with whom you're talking to. You don't know anything more than the initial BitTorrent header. So this is a very complicated pattern. So in a way, troubleshooting, what we call troubleshooting here, is mostly for troubleshooting simple communication, not for troubleshooting complex communication. In the worst case, you will be troubleshooting a set of communication one after the other, like an iterative process, like when you do with DNS resolution. But it is very unlikely that with tools like Wireshark, you're able to decode or to dissect this type of problems. You usually don't have those problems because you will try to understand communication per communication what is happening. But this type of communication are also very challenging, that put a lot of effort on the human that is trying to understand what's going on. I'm not saying it's a limitation of Wireshark. I'm just saying that the human part of the problem is very important. So Jasper, yesterday, 2 days ago, has shown a sort of smart interpreter, let's say, of the TCP traffic. And it's good. It's good. We need tools like that. But on the other hand, the human part of the story is still very relevant. It's not that humans are not that important because the tool is doing everything on our behalf. That's a very important point I want to make. And also the cloud and content delivery network are changing the pattern of the traffic. Because the problem is that there are many people that want to access the same content, probably at the same time. So when Apple is delivering the new iOS update, everybody's clicking update, update, update. So all at the same time, across the world, we have to find a solution. And content delivery network or other type of cloud-based computing are trying to address those problems. So the point is that you don't know the IP of the server you're talking to in advance. So the usual Wireshark IP host, blah, 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 filter doesn't work. So you have to capture everything. And later, to follow that type of communication. And also, we are moving towards a software-defined network, so something a bit more dynamic than what it used to be. So in the past, when I started with Linux, and there was a new Slackware distribution, so you know that you have to filter the Slackware IP address. At most, they're balancing the traffic across 2, 3 machines. But here, the story is totally different. It's totally different because you have some big servers on the internet that are serving customer 1, customer 2, customer 3, so the IP is the same. And filtering on IP address does not help. Because if you filter on IP address, it might be that the same node, so the same Amazon node, let's say, so the same IP, that is in a way optimal with respect to you, because it's close enough to you, it has the data you're looking for, it is serving both Amazon Video and Apple iOS download. So probably this is not the best case, but this is to say that IP addresses are not that relevant because the same flow coming from a certain node might be used for service A and service B, and those communications are encrypted. So many times it is very hard to find what service is asking what. And sometimes when you have to monitor the cloud, it is better to move your tools on the cloud. So the first day here at SharkFest, we have seen a presentation exactly about that. So if you have your resources on the cloud, you cannot, from home, connect to the cloud and do a remote Wireshark. I mean, you can do that in theory, but in practice, the best is you to move your monitoring infrastructure also to the cloud, where the traffic is flowing. And this is very important. But another point to take into account is that when you want to monitor a customer access to your cloud-based infrastructure, sometimes you have to impersonate the user in order to understand the real user experience. So you have to be at the customer premises, let's say. And the advent of the cloud has changed a few things. Okay, first of all, based on your location and network connectivity, you are accessing a different service. You can make a test this morning. So you go to a certain server with your 4G provider. You go to the same server using wireless, and it is very likely that you will be using different IP addresses. So sometimes it might be that the communication is good with one provider and is not good on the other provider. So this means that the address is not persistent. So it means that when you want to troubleshoot a certain service, you cannot know in advance the address. So that's why it's very easy, it's still very popular to see companies, you have seen a few of them here, that allows you to dump everything sometime in the cloud, and then based on that, you start troubleshooting the problem. You will see the first communication is with server A, and server A is asking you to go to server B, and so on, and so on, and so on. So it means that if you use Wireshark, it is not that simple. So if you want to troubleshoot, I don't know, Netflix.com because your Netflix video are not that good, and put IP address equal, doesn't work. Simply doesn't work. You have to do some sort of human analysis first before doing that. I also want to show you another interesting example. I have a few servers. I made a few tests. This is you can recognize that from the name here. So I'm trying to access Facebook from my machine hosted at DigitalOcean. So this is the IP address. You see, you will see that with this IP address, IPv4, IPv6, if you do a trace route to Facebook, I make a certain path. But then at the end, when I do a ping, you will see that the latencies are very low. Okay? So it is less than a millisecond, or about 1 millisecond, in theory, for DigitalOcean. And then I take another example with another provider with my ADSL at home. You will see 66 milliseconds. Let's look again at the IP address. So we see, let's look at the IPv4, that it's easier. So it ends 6435, okay, from DigitalOcean. 8636. So it's the same Facebook, but it's not exactly the same Facebook host. So I see the same content, but the IP address is different. Let's make another example from another host. Again, DigitalOcean was less than a millisecond. The other one was about 50, 60 milliseconds. This one is 6 milliseconds. And the IP address is slightly different, but the same as this one. So this one is different. So this one is in the Netherlands. It's in Amsterdam. And these two are in Italy. So even though they are different providers, the IP address is the same. Okay? But looking at the traffic, okay, and thinking about Facebook as an American company, so something comes to my mind, but this is very strange. How can it be less than a millisecond? It looks like I'm sitting next to Facebook, so Facebook has an host next to me, so in the same LAN. How this is possible? So can I trust the IP address? That's the second question. And some months ago, I've seen a post from Gerald on Twitter saying, hey, I want to improve my Lua skills. So I've written this Lua script. You can confirm, Gerald, right? Just to calculate the distance of an IP in terms of time. Okay, you can put it on Wireshark. You can see this very nice column here. So in essence, if you go to Wikipedia, you will see that it explains that. So in essence, the propagation theoretically is at the speed of light, but for radio signal, depending, or for electrical signal, depending on the communication media, you will see that it's not exactly that. So it might be that it's 75%, let's say, of the theoretical speed, 65, and so on. But just to give you some very rough numbers. So on a LAN, it's less than 5 milliseconds, usually much less than 5 milliseconds. On the same content, it's about 20, 25. So I mean, if from Italy, I ping Germany, I ping Switzerland, it has to be in that order. So if I pass the Atlantic, it will be probably 100 or something like that, based on the West Coast, East Coast. It depends. So I made another script based on Gerald and Wikipedia code. And I've seen that based on these three latencies going, again, against the same Facebook, you will see that based on my tree provider, the distance is very different. So the thing is, where is Facebook? That is the main question. I have implemented the same thing in NTOP, that is the open source application I was talking at the beginning of this talk. So where is Facebook? Why Facebook is reporting me a very different latency according to the provider I'm using? It cannot be that Facebook is next to my DigitalOcean $5 a month virtual machine. I don't think so. It will be too cheap. But I cannot even think that it's 24,000 kilometers away from where I am. So that's why I said, let's look at the cloud. Let's try to understand first, before looking at our packet traces, what is happening in the internet today, and then be able to interpret those data based on that theory. That is very important. So if you go to peering.google.com, just to give you an example, but many other companies are doing exactly the same, you will see that they have created the internet in a sort of donuts. So this is the Google data center, so where real data live. Let's say US, okay? Sunnyvale, these places. And then you have other points of presence that are more distributed across the world. Might be that there is one in Vienna or another one in Zurich, probably. There's another big data center for Google. And then there is me here, sitting in this room, in this hotel, connecting the Wi-Fi to Google. I want to read my email. So they have created another layer here, another donut, okay, that is implementing caching and services. The same for Netflix, the same for everything you want. I mean, those big companies. So in essence, in the past, I was talking directly with the center. So when 20 years ago Google was created, probably had a few servers around the Bay Area. And then they started to put regional servers and so on. And now I'm not talking with Google anymore. I'm just talking with the cache of Google. Internally, Google somehow talks directly with the rest of the data center. So if you move to the other page, so if you scroll peering.google.com, you will find that those edge nodes are kind of everywhere. I mean, everywhere that makes sense, of course, where the internet population is living. And this explains many things. This explains why, when I connect to Facebook, I will see less than a millisecond latency. Because the Facebook I'm thinking is not here, okay? It's not here. But the Facebook I'm thinking is probably, again, this is Google, the other is Facebook, two different things, but just to give you the idea, probably have a local cache that is very close to me. I'm talking directly with the cache. I'm not talking with the remote address. And telecom operators, in a way, are using this technique to attract their customers. So if I ask my daughter, that is 13 years old, if the internet is working, she's not opening a terminal and doing a ping. No, she's connecting to Facebook. She's connecting to Google, to Gmail, to YouTube, to whatever you want. If YouTube doesn't work, if you cannot reach Google, it means your network is down. She's not asking herself, first of all, because she doesn't know, but she doesn't want to know. So I trust more fast.com, where I want to check the internet speed, rather than my old Unix, whatever, tricks on the command line to understand that. This because those points of presence are that distributed, there are so many, and that telecom operators must take this into account. So if you are a telecom operator, in a way, you have to pay a fee to those big guys to have their content servers in your network. Because even though you have a great connectivity everywhere in the world, but if you go to Facebook, to YouTube, and your video is flickering simply because you don't want to pay this fee to Google to have a local cache, then even though you're super fast, you're bad. Because most of the users today are testing your speed with YouTube, with Facebook. That's a matter of fact. So when I see people still talking about millisecond ping, in a way they belong to an old generation, like me. So it is very important to take this into account when we troubleshoot. And don't think that one host is one host, because those hosts are everywhere. And a good way of implementing that is through a technique called Anycast. In the past, when I was a student, my teacher said, one host, one public IP address. Anycast is exactly the opposite. Initially used by DNS, the idea is the following. You provide the same service using the same IP address, and the routing protocol will do the magic. You know that in routing, you can access a destination, through multiple paths. And based on the weight you put on routes, you will decide to use route 1 or route 2. So in essence, Anycast, playing with those techniques allows you to have the same IP address, 1, 2, 3, 4, like I showed you with Facebook before, in multiple locations in the world. So the IP address will be the same. But based on routing, you will accessing the best route for you. So if I'm in Austria, if I want to access 1, 2, 3, 4, might be that I'm talking with the server in Vienna. But if I move to Italy or to Munich today on my way home, I will be accessing the same 1, 2, 3, 4, but talking with the data center in Munich. Everything looks close to me, even though I'm not talking with the same host. So that's why I'm saying when in Wireshark you filter for an IP address, think first if this is the IP address you have in mind, or if this IP address might not be the same IP address. Another good thing that people do is say, send me your packet capture. You have a problem? Okay, send me your packet capture. But if you try to repeat the same experiment from your network in another location, again, you don't have to go across the Atlantic. But moving from here to Munich, so that it's a 40-minute flight, changes completely the scenario because, again, when talking with those big guys, if you talk with my ntop.org single host, that's not a problem. But talking with these guys, you have to think that the network topology is not the same network topology that the other guy is looking at. So, again, it's not a limitation of Wireshark. It's the human that has to ask himself whether the data Wireshark is displaying you is the correct information, or if it has to be interpreted first before taking a conclusion. So in essence, through Anycast, you replicate the same IP address multiple times, and the routing protocol will do that. And CDNs are heavily using Anycast because, first of all, you show people the same IP address. That is great. So in the past, when I was working for IBM 20 years ago, my IBM email address was Luca Deri at zurichresearchlab.ibm.com. If I was talking with my American colleagues, it was almaden.ibm.com. And somebody decided to leave Almaden because we want to see Europe. So you had to change the IP address, the email address, because it was not whatever Luca at Almaden, but Luca at Zurich. Because the IP address, the email address, contained a way to distribute email across IBM. But now, today, you will always see facebook.com because, again, people are dumb. People don't want to think too much. People want to remember simple things. So you want to put www.google.com, and wherever you are, the network has to do the magic. And Anycast is also helping you with distributed denial of services attacks, because if I'm here, I want to attack, let's say, a big CDN, I will not attack the whole CDN, but I will attack the IP address that the routing will show me. So I will be attacking probably only Vienna, even though in the past, or if you want to attack ntop, that is, again, as a few machines, you will be attacking the real destination. So to make this long story short, CDNs are good, but remember that IP addresses are not meaningful as they used to be. Again, it is. Latency is crucial. It's really important. But when you see, and use the Gerald script and put it in Wireshark, when you see that the latency is suspicious, and Wireshark is showing you the latency and the location using GeoIP. If those two things are not, let's say, compatible, okay, it's not the bug of Wireshark, but ask yourself why, and very likely you're talking with a local cache and not with the remote end that is in GeoIP. So packet analysis people must remember that. So the conclusion here is that Wireshark is a good tool, but you have to interpret the results. You have to see if the data that is displayed by Wireshark is correct. If you're in a LAN, those problems don't exist. So yeah, A is talking to B. Of course, everything looks simple, but if you want to do troubleshooting with this type of traffic, you have to take this into account. And just to complete my tutorial-like introduction, just remember that even though everybody's talking about the cloud is very small. It's very, very small. Most of the things, interesting things that are happening and where the troubles are in the green area, at the edge of the network. Because at the edge of the network, communications are very interesting. So we will see a lot of problems. So the cloud is working. So again, if you want to ping, don't ping. Open YouTube, okay? Because you assume that YouTube is always working. So most of your problems will be there at the edge, so where your users are. And this is also where you have the variety of communication, Wi-Fi, wireless with mobile phone and so on, that most of the problems are. And we need to control the edge, because the edge is also the place where IoT is creating a lot of troubles. So that's very important. So why IoT has changed an interesting part of the internet? Because when the internet was designed, it had a middle-age approach. So good guys are in, we put a big fence, a big wall, bad guys are outside, okay, and you start to divide the world in these places. So you see, this is the internet. Oh, these are the good guys. If I have to expose something, I will put you on DMZ. Remember that story? So there are firewalls, blah, blah, blah. And also many other things. So the theory said physical security is the #1. But now, things have changed, because if you go here on the corridor, you will see the access point are placed on the ceiling. You can disconnect the access point, turn the access point, look at the MAC address, and put another machine that is impersonating the same access point that it used to be. So you are no longer putting your services in a very controlled environment. And because of that, also looking at the MAC address or IP in certain communications, let's say, might not be a very good idea. Now, after this introduction, I want to show you some traces, and I want to show you in practice what I meant when I told you those things. Again, if you want, you can play with those traces with me, or you can play with them at home. But now I want to show you practically, okay, why these things are relevant. Again, think about the current trend. Go to shops like MediaMarkt or consumer shop and look at devices, okay? People buy very powerful devices. So if you think that a standard television that costs 200, 300 euro, maybe as a quad core or more, CPU, wireless connectivity, connection to Netflix, to this and that, you will realize that even a device that is not that expensive today is very complicated and creates, I don't want to say challenges or problems, but let's say create connectivity patterns that are kind of unexpected. And because of that, people, at the moment, they're forced to plug the power cable, and everything else is automatic. But I believe that in the past, the power cable will be removed, So you buy television, you put it somewhere, and there will be an electricity, something that is giving electricity to your television, and that's it. Because people don't want to think. People want to consume, or at least the companies are telling people to consume the product without doing much. Because of this, it means that the television must be smart enough to understand what is happening, to tell the firewall, I want to do this, and the firewall will say, OK, UPnP grants you that, connect to the Wi-Fi network, and so on. So, and this is very important, because if you look at small devices like Amazon Echo Dot or the similar device from Google, you will see that those devices don't have a display, don't have anything. So they have to be simple to connect. Okay. That is also very important. And another problem is that people are using smartphones for everything. Think about yesterday, at the game of yesterday. So you download an app here, and you want to access your device that you acquired for very few euro at MediaMarkt. So let's make this example. Let's look at this camera. So this camera is something we have in our office, and I want to put the camera in the office. In the past, so if I wanted to have a camera in my office was accessible from the outside, I had a few options, but not that many. Option 1, VPN camera. Option 2, put on the DMZ the camera IP address, connect to the camera. But people today want to buy the camera. Again, at most, they want to plug the electricity and then download the app, click on the app, and see the camera. That's the story. Because of that, some compromise have to be made. So if you think today at cloud devices, you will see that the traffic patterns, and when you analyze that with Wireshark, is no longer going from here to here, but is talking with the cloud. So in essence, there is a meeting point here somewhere, and my phone is talking here, my camera is talking here, and then we do this interconnection. Now, it's good, right? So you open your camera, you will see what's happening. But there is one problem. The problem is that system administrator and network administrator in the past had a lot of power. So you had to be good guys, good friend of those people, because whenever you need something, they have to do. Now these guys have lost most of their power, because it means that here you can install a camera and you can enter a trusted network without asking anybody to do something for you, special for you. And the security policy is not decided by our friends, by our colleagues, but by the cloud. And if you open those cheap products, so this one is a D-Link camera, but you can have many different examples, you will see that because of the price, they want to keep the price down, the consumer devices, probably the professional devices not, but the consumer devices very often are not manufactured by the company that you're buying. So if you buy a brand X camera, and you look at the traffic, you will see that this camera is probably manufactured by another company that is doing the same camera for various companies, just changing the case or the color or the logo, the brand. So the cloud itself is not managed by the company you are trusting, because as a big name, but is managed by other people. That's very important. So you are giving your security to people that you don't know. Yes, and this is the message. So let's look at the traffic trace. So this is my camera, okay? So we have the camera in our office. We are accessing the camera from remote. Forget the Italian, that's not very relevant. So in essence, I talk with my camera. I'm from home here, so I'm not at the camera. So the thing I have to do, I have to click on my D-Link. I put my email and password. Somehow, I connect with the camera, okay? So that's the result. I can do the same with my laptop. So if those of you who have downloaded the camera, the pickup, so this is the traffic that I have captured when talking with the camera. Again, remember the first slides. Initially, the internet wasn't clear. Everything was simple to troubleshoot and debug. You know exactly who's talking to who. Now, if you open this file, you will see those communication, those conversations. Again, start Wireshark, double-click, connect to the camera for communication. I didn't put address resolution here, but if you put the address resolution, you will see that I'm talking to Amazon. Again, depending where. So nowhere in my traffic I see the link. I see Amazon. But again, if you mix this traffic with other types of traffic on your laptop, it's already making things a bit complicated. So here, if I want to see what my camera is doing, I cannot tell you. The only thing I'm telling you is that if you think here, I leave the screen open for a while, okay? So I see the camera. The main flow that I see is this one. So I can only speculate that this one is video because it's increasing. But I don't know how the authentication, how the rest is working. Take the camera.pickup, open it with Wireshark. Forget about those ports. Don't be fooled by those ports. Don't see 443 encryption. Look at the traffic. Follow the traffic, or do a strings of camera.pickup. You will see that inside the traffic, there is a lot of personal data. So there is my account, my everything. So if I see 443, or if I see this type of protocol, here I cannot speculate if this is encrypted, but this has to be encrypted. And when you see 443, you will see the lock on your bar. You feel yourself safe. Oh, good, I'm using SSL. Only for the first communication, but because if you open the camera, the pickup, you will see that here your credentials are in clear. Look at the pickup. The pickup is part of the distribution. So users feel them secure, even though they are partially secure. Because of the economy, because of the cloud, because the way it works, you have opened your network to unknown people, and the initial part is SSL, but the rest is not SSL. And your credentials are not saved. And you don't know what is happening. You just know that probably the stream, that is the video stream, is the last one, simply because you see the bytes, but not because you will see more than that. And with IoT, this is very, very standard. If you buy thermometers, or if you buy small things that are monitoring something, usually they talk with platform like ThinkSpeak. So those devices are doing a post somewhere, send my data, send my data, send my data. And then when you open the mobile application of your device, you are accessing the other, so the same cloud-based storage, because everything you have is somewhere there. This is a very common pattern. Let's make another example. Let's try to clarify this. So if you have coffee machines, okay, or vending machines, in the past, each vending machine, so suppose that you have to put coffee to make sure that there is coffee on those machines, right? So either periodically you go to the coffee machine to see if there is coffee, like here, they are doing some from time to time to check the coffee, or you put a SIM something, and you have a gateway somewhere. So Deutsche Telekom, Austria Telekom is making sure that you're talking only with your devices and nobody else can talk with your device. So even though you don't have a password or something, nobody else can talk with that, but because you're talking with the controller and the gateway is talking with your devices. But now things have changed because you have the cloud. This doesn't make any sense. So you put a SIM that is talking to the 4G network, if not Ethernet. This one is talking with the cloud, and you have a different privilege for the owner of the devices or for the waiter that has to check if there is no coffee, so has to put coffee. And very likely, my coffee machine is sending me an alert saying, I need more coffee, or I'm running out of cups. So this is the way it works today. So in essence, if you think about IoT, you will see that we have the IP address. So we have very, let's say, simple sensors. At some point, there is a gateway that is interfacing the internet with the simple part of the story, okay? And this one is delivering our data to the internet. So last May, I wanted to buy a Powerwall, a Tesla Powerwall that is a battery that is talking with my solar roof panels that allows me to stock energy so that at night I can use my own energy, or I can try to optimize the way, let's say, I produce electricity, right? So I bought this device. This Tesla was installed. And when I installed it, I said, oh, great. So I have a phone application, so I can check, so this is the way Tesla works. So at the moment, when this picture was taken, I was producing almost 1 kilowatt that was sent a part to Tesla to refill the battery, and a part to my home for my own home consumption. So I have this very nice mobile application. And when the Tesla was connected, the guy who has installed it asked me to connect it to the internet through Wi-Fi or through Ethernet. And so I did. He did the installation, and then I disconnected everything, including the cellular, because the Tesla comes with a cellular SIM. I don't have to do anything, and no password, nothing. Mr. Tesla is taking care of that. So I disabled that. 2 days later, somebody from Tesla Italy called me and said, hey, your cellular is off. I said, I know. Why that? Because I connected this to my network. So I put my cable. I'm able to do curl something to read my energy. I don't want that somebody from the outside comes to my home. Okay, Tesla is a nice brand. I mean, I have nothing against Tesla. But I don't want to do that. To make this long story short, 2 days later, cellular was on. I didn't do anything. So Tesla, I gave up. So it's now on all the time. I had to disconnect my Ethernet, so I am not monitoring my power consumption just because of that. So when you buy those devices, make sure that you understand that you are paying a price for the device, but at the end, you are creating a problem to yourself, because you're bringing to your home a Trojan horse. Like when you see people that are connected with a wired cable, and they're connected to the wireless of the neighbor, let's say, hotel. So you put your super costly firewall, and then you're opening a problem simply because you're sitting next to a neighbor that has open Wi-Fi, and you forgot to turn the Wi-Fi off because at home you need Wi-Fi. So your PC is connected to your super safe network at the same time with an unsafe network. So this is exactly an example. And the way Tesla is managing security, again, there is a pickup inside the folder I've shown you. It's called Tesla.pickup. The way Tesla is enforcing the security, so trying to make it more secure, is the following. When the Tesla battery is resolving the Tesla address, it's not using my own DNS, but it uses some DNS that are hard-coded inside the Tesla battery, because the Tesla, of course, is updating automatically. I don't know. I simply can tell you that I paid for the Tesla, but what is happening with the battery, I don't know. And this is something I can sniff on my wired network, but I don't know what is happening on the cellular. So the only thing I'm saying is that if you look at Tesla.pickup, you will see that Tesla is trying to resolve the addresses only from specific DNS. And in order to do that, they have disabled recursion. And because of that, they say, OK, I know that I'm an IoT device. I know that I'm kind of insecure. I'm trying to connect to the internet. But to what IP? To the IP that some DNS I trust are resolved. So think about HTTP and DNS I showed at the beginning. So the trend of trusting somebody is becoming more and more important. So Tesla wants to resolve the addresses only from DNSs that they think are good, even though the Tesla is asking for public IP addresses. So see, they're asking for this Synergy, Tesla Energy.services. So the way the DNS is used is also no longer the standard. So you don't go in the control panel, you put the DNS. But based on the application is trying to use its own DNS because they have implemented a portion of the internet inside the box. The last example I want you to look at, so there is a packet trace called smarthome.pickup. In that trace is a very simple example. So I have a friend of mine who likes this type of toys. And my friend bought, he's not blind, but he's mostly blind. So he has brought this Alexa Echo Dot that has connected to the rest of the home so that he can tell Alexa, hey, do this, do that, turn on the music, turn the heater, these type of things. So if you look at the pickup, I put here your the IP address for your reference, you will see this. There is the Alexa Echo Dot. There are the smart speakers from Sonos that are another interesting example. So this is a speaker that connects to the internet. So if you want to bring this to your home over the mountains with no internet, they don't work. So remember this before you buy a Sonos, because Sonos want to talk with Mr. Sonos, and then if Mr. Sonos says, okay, you can work, the loudspeaker will work. And then my friend has another device called Logitech Harmony that allows him to interact. So this is an infrared-based controller that allows to interact with the devices that are not smart. So he has a television that doesn't have internet connectivity. So this one is a vacuum cleaner. It's a Roomba. So you will see another IP address in the pickup. And this one is a weather station. So I made a small experiment because he said, oh, you come to visit me, I want to show you these things. Okay. So in my mind, I'm not that young anymore, right? So when I said, Alexa, play a song on Sonos, I thought that if I start Wireshark, I would see a communication, Alexa, Sonos. So the same when, hey, turn on the Roomba and clean the kitchen. I thought that this was the pattern I wanted to see. But it's not like that. Even though those devices are very close, so the Alexa is here and the speaker is over there or in the other room, they don't talk directly. Think about binitial slides. Think about filter pair IP. They don't talk. So if you do a port mirror on the switch, and most of those are Wi-Fi, so you must be lucky enough to have an access point that allows you to do this type of things. You will not see the traffic, at least that I expected. And also, another interesting story is the following. When you have to enable those devices with Alexa, in essence, what you do is the following. You install the device, and you have to install what Alexa calls a skill inside the Amazon cloud. And then on the Amazon cloud, you do the connection between this device you acquired with your account. And this is a sort of driver, let's call it, for Alexa. It's not a proper driver in the term that we are thinking about, but this one allows you to control from your Alexa this device that can speak with Alexa. So in essence, now if you have a print, you connect the print to your Windows PC, the driver is installed locally. This is not the driver, but it's a sort of driver for the cloud, okay? So your Alexa device you have in your living room will talk with that. And when I said, I don't see the traffic pattern I expected, it's because when I tell Amazon Echo Dot, that is what we call Alexa, when I say, hey, Alexa, turn on the heater, or Alexa, turn on the light, or Alexa, play a song there, what it happens is that Alexa is speaking with AWS. AWS is looking at my account, and then through those skills I was talking, they're talking back to my device. So in essence, if I am in Vienna, I have Alexa here, I have my speaker there, I have to speak with Amazon in Ireland, let's say, to turn on a device that is 2 meters away from me. So that is the story. Now, if I look at the security, or if I look at the traffic, look at smart home. Look at smart home pickup. This is an interesting example. You will see that there are many devices, okay? So you can figure out some of those by the manufacturer. So this is the weather station, okay? Or this is the Sonos. My friend has a few Sonos devices. And you will see that, again, you're not able to interpret the traffic looking at the traffic because everything is encrypted. So if I look at the same, so open the pickup with NTOP NG, so our application, you will see that we are able to put a device next to it, because looking at MDNS traffic, I know exactly how the device is advertising itself to the internet. So for me, it's not an IP and a MAC, but for me, I know exactly what is that about, because inside the MDNS traffic, I know the nature of the device. I mean, as long as I can trust the device. And now, inside this pickup, I said I wanted to capture, okay, the time that I said to Alexa, do something, okay? And then I created small pickups that allows you to see this traffic pattern. So instead of letting you do complicated things, I have created a small pickup called Alexa Sonos Only that allows you to see the interaction between Alexa and the Sonos, and in particular, when I ask Alexa to play a song on the smart speaker, just to show you what is happening, okay? Just to show you that what I told you at the beginning, don't think that the Wireshark is unable to see the traffic. Wireshark is working very well, but you have to look at the Amazon AWS traffic. Don't think that those devices that you know the IP address, so 122 and 172, are talking directly. So if you look at Alexa Sonos traffic, okay, in the Alexa Sonos traffic, I have captured the traffic that I see when I told Alexa to play a song on the Sonos. And I open it with Wireshark. So if you can put the same display filters as I did that you can find on my slides, you will be able to color here. You will see that those devices keep persistent communication with AWS. Again, they are really encrypted, so I don't know what is happening. I can tell you that I know exactly that at this time, and if you can enlarge the interval, you will see that better. So at some point, I asked Alexa to play a song. So what is happening when I ask that? You will see that Alexa, so the red one, again, you have to zoom. So if you open Alexa Sonos only to pick up, you have to change the interval. You will see that when I tell Alexa, play a song, Alexa is talking with Amazon. So you will see a peak of traffic. Again, everything is encrypted. At the same time here, you see, green, you will see that the Sonos Cloud is talking more, let's say, with my speaker. So it means that on the previous slide, I've shown you that through the skill, there will be a sort of interaction between my devices on the Amazon AWS, not directly on Amazon. So the device is doing something here. So you will see that it receives a command or something like that. And then the music starts. So what I'm saying is that when you have what I call IoT or smart devices, so this type of modern device that you can buy, and if you want to analyze the traffic, you have to know that those devices, like in the past, are not talking directly. So you should not put in the middle a tab to see what they are doing, because they don't speak. So you're talking with Amazon. Amazon is talking with the Sonos Cloud. The Sonos Cloud is talking with my Sonos speaker. And then the Sonos speaker will play a song from a NAS that is connected in my room. Or if you want to make this thing even more complicated, you can play a song from SoundCloud, from, I don't know, another sound provider to make things more complicated. So at the end, the last communication you will see is from my Sonos speaker to my NAS because the song is there. Otherwise, everything else is on the cloud because, again, remember this picture. Remember that the interesting part is the internet gateway. It's on the internet gateway that you will see those devices interacting because they speak with the cloud, and on the cloud, they receive the command for playing a song. Okay? So don't look at direct communication because they don't exist. But again, I provided you the smart home.pickup that you can play with at home, so you can see that what I mean is relevant. It's becoming more and more relevant in our devices. And before I conclude, I want to show you something that is very, very interesting. When I told my friend, but what can I do? What type of firewall Amazon allows me to have on my device? How can I make sure that, let's say, I can play a song, but my son cannot play a song, or what type of security feature? And the security is very limited because everything is managed on the cloud. So when I see that the most you can do is, for instance, you can disable Amazon Dash. That is a small device with a button. So the only thing you can do is disable Dash. So it means that you cannot tell Alexa, buy me 2,000 books and send them home, right? This type of things. That's the most you can do because Amazon is relying on people who create those skills to be good guys. But you know that those manuals don't work much because otherwise, if those manuals will be enforced, we will see no malware or all these type of things. So what I'm saying is that we have to pay attention whenever we connect those devices because looking at the traffic, I don't want to say that it scares you, but in a way it does. So just to wrap up, go at the beginning of my talk. If you're interested, look at those pickups, and you will see that, in essence, there are a few things that I want to remark. Okay, first of all, those devices, some devices, contain a mobile SIM. If you buy a modern car, especially the expensive one today, BMW, Mercedes, and so on, they have a SIM, okay? In a way, you don't have to pay for the SIM. It's not the fact that you don't pay a monthly fee, your device doesn't have a SIM. So I don't pay anything for my Tesla. I just bought my Tesla. But the thing is that here, so you are kind of controlled. So the owner of your device is not you who paid for it, but the manufacturer, right? In a way, this is good because it is providing you a service, but think what happens if somebody is breaking those manufacturers. So what happens to your devices? In the worst case, my Tesla will not operate, but think about a car. There are this type of concerns that, from a point of view, are very important. HTTPS is no longer enough, let's say. First of all, because we must have some features like certificate pinning, so to make sure that the SSL certificate is coming and is signed by the person I'm talking to. Okay? You have seen that very, very bad things have happened in Syria, for instance, in the past few years when some certification authorities trusted by our browsers were not doing their job very well. So in essence, they have given to this Syrian government the ability of decrypt SSL communication. And the browser was putting you the green lock. Hey, it's good. But the fact that the lock is green does not mean that you are safe. It means that the certificate is coming from somebody that the browser trusts. But if this guy is not very good, there are some problems. That's why if you use a mobile a mobile application, let's say a mobile version of Messenger, you will be talking exactly with that messenger, and it's hard-coded inside the application that I want to see exactly this certificate. Whereas if you use a generic browser, you will see the lock that is green, but doesn't mean much. I also remember one of the first pickups I've shown you about my camera. The initial communication is in SSL, and the fact that you see the browser in SSL does not mean, and use Wireshark for doing that you are safe. Because if you look at the video stream, the initial communication is in clear. So don't trust the logs, okay? Here's another thing. SSL is good, but it limits inspection. Think about my IoT devices. I don't know what they are really doing. I don't really know. I don't know if my Amazon Echo Dot is recording my voice and sending it to somebody. I don't know. The only thing I'm saying is that he's talking with Amazon. Also think about alternative connectivity. When you have a super protected network, you spend a lot of money with the smart firewall, and you connect one of those devices that might have an alternative communication. Again, if you look at the box, it's not written anywhere that there is a SIM. If you connect to it, if you SSH to it, you will see that. But this can create interesting problems for the system and network administrators because your connectivity is no longer the connectivity you are monitoring, but there are other ways of circumventing that just to make easy for the user to understand what's going on. Because if you look at your Tesla app on your phone, you are happy. But at the same time, this is creating a few problems. So this is all I wanted you to play with those pickups. Think about that, let you understand that, unfortunately, internet monitoring and troubleshooting is becoming more and more complicated, and the human part is becoming more and more relevant in this new internet. Thank you very much.